So section 3.2 is addition of whole numbers. In 3.3 we're going to do subtraction. And 3.4 is going to be multiplication, and 3.5 is going to be division. So our four basic operations. So today's subtraction of whole numbers. So first, by definition, or a definition of subtraction. For any whole numbers a and b, where a is bigger than b, a minus b is the unique whole number c such that b plus c is equal to a. So if I throw some numbers in, it's going to make a lot of sense. The reason that we take 5 is greater than 2, for example. If I get 5 minus 2, my answer is 3. The reason is because I could take this, and if I added 3 to the right-hand side, they'd be equal. That's all the definition said. So if I add it to the side that's got the smaller value, they're calling that the value b. They wrote them in backwards order of what I just did. I apologize for that. There's their smaller value, and they add the number that's the answer to it, 2. They get back to the original larger value, in this case 5. So that is the subtraction model, or the subtraction definition. We're going to look at 3 different models, and as we look at these different models, I'm actually going to need you to be able to be nearby your group people. So let me pause for just a moment and have you shift to where your group people are. I don't know that we've assigned new group people, or if I did, I just did it we did it once. Is that true? Okay, so I'm going to pause the video and I'm going to let you guys shift, and if you don't know who you're supposed to be with, I'll let you know. All right, thanks for finding your people. We're going to take a look at 3 models of subtraction, okay? So the first model for subtraction is the takeaway model, and in fact, if you were to ask a lot of children what does subtraction mean, they might use the phrase takeaway. So we're going to find very quickly that that's not the only way to think about subtraction, but it is one way to think about subtraction. So Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? So with the takeaway model, you always have something already, and then you're removing a portion of them. You're taking something away. So if we were doing this one, we're going to draw a picture of what's happening. So I'd like for you to draw a picture of 24 rocks. Well, I wanted it to be thicker than that. Let's try again. Okay, I have 24 rocks. My rocks are brown. And Eli sneaks in and he takes 4 of them away. 5 of them, did it say 5? Yeah. 5 of them away. So here are 5. They get removed. And we count the remaining set, especially if we're working at a young enough age, we would count this. And how many rocks do we have left now? 19. So my answer will be 19 rocks. Since I do have units, I will include them. So with the takeaway model, I always have something, and then I'm removing a portion of it. Another model is missing addends. So missing addends is the idea that I don't have everything to start with. I'm missing something, hence the word missing in the description. Lisa needs to collect 10 leaves for a school project. She and Temeskin go and find 8 leaves. How many more leaves does Elise need? So in terms of a concrete picture for this, I'm going to draw my leaves. I already have 8. Okay, there's 8 of them. They look terrible, but we're going to pretend anyway. I have 8 leaves, and I'm supposed to have 10, right? So what I need to figure out is how many more I need to put into this system in order for this to actually have 10. So what are the missing numbers of leaves that I have? Yeah, there are 2 missing leaves, and we draw them dotted. That's not just a convention of my screen. You don't have to draw them. They can look a lot more like leaves on your paper. I just don't have a tool that does that. I have circles and ovals and stuff, so that's what we got. So those dotted ones are the ones that are missing. So this is what a concrete model for this would look like. If you were looking at an equation type model, it would look like this. Whoops, I meant to do an 8 here. And I would have a missing piece here, and then I would have the number 10 that I want on the other side. And the answer would be 2 leaves in between. So this is a concrete model, and then this one would be an equation type, or concrete picture and then an equation picture. And the last one is a measurement model. So once again, we encounter something where we're not working with decimals and fractions. I understand that. But the quantities that are being expressed have the ability to have a decimal or a fractional amount. And that's why it's a measurement model. So in this case, it's miles. You can drive a fractional number of miles, a decimal number of miles, right? That's why this is a measurement model. Akeem drives 15 miles to the mall. As he's on his way home, his mom calls to ask him where he is. Apparently does not have Find My Phone or Life 360 on his device. So he states he's coming home and has driven 8 miles so far. How far is Akeem from home? So when we're doing this one in terms of a picture description, we're drawing a number line model. And if you want, you can draw your pictures in here. Here's the home. And over here is the mall. I don't know. That's the mall. We got the big mall over there. And what we know is we know that they are 15 miles apart, right? So this whole thing is 15 miles. Akeem says he's driven 8 miles so far. So he's coming from the mall backwards. And as he comes backwards, this distance that he has driven so far is 8 miles. And the question is, in this particular scenario, what's missing to make up the full 15 at the bottom? So I have a portion on top that's 8. This portion right here, that's a big old question mark, right? And then I have the 15 on bottom. So what number needs to go in that question mark place in order for my 8 and that number to equal 15? Yeah, 7 miles. And again, if you want to look at this, this is a great picture kind of view, right? A concrete picture of what's going on. If you want to look at it from an equation standpoint, much like the last one, because this has a missing piece, you're welcome to write missing piece plus 7 has to equal 15 from an equation standpoint to see the same picture with just numbers involved.
That 7 should just be an 8.
Oh, I'm sorry. Thank you. It's supposed to be an 8 there. Yes, you're right. Perfect. Okay, so what you're going to do now is you're going to create 3 models. You're not solving anything. You're just going to create an equation. And it says for each of the 4 models, I apologize, change the number 4 to the number 3 in your directions. There used to be 4 models, and then the textbook changed and they eliminated one of them, so that's fine. We now only have 3 models for subtraction. So we have takeaway, missing add-ins, and number line. And the real difference between these models is not the process of finding the solution. It's how the question's originally worded. Okay? So I need you to word a question where it's clearly a takeaway question, word a question where it's clearly a missing add-ins question, and then word a question where we have a number line question. Okay? So now in your groups, that's what you're going to do right now. All right, let's take a look at what you have. I would like a volunteer, 2 volunteers actually, 2 groups, to volunteer to tell us what your takeaway model says. Emily and Hallie.
We said if Emily had 8 nuggets from Chick-fil-A, Gracie took 2 away, how many nuggets does Emily have now?
That's a takeaway model. Very good. Yes. Hallie, what you got?
We said Molly had 10 pieces of gum, Bethany wants a piece, as well as Sally and Emily. How many pieces does Molly have left after sharing?
Excellent. That's another takeaway model. Okay, wonderful. How about missing add-ins? So you guys are, both your groups are finished. I need from among the last 3 groups, I need 2 volunteers to do missing add-ins. Monica?
Julie has 20 classmates. It's her birthday and she wants to bring cookies. She has already made 12. How many more does she need to make?
Fabulous. So she needs a certain number of cookies. She's already made so many of them. She needs a certain number more. That would be missing add-ins. What do you have, Jenna?
Reggie needs 3 puppies. He has 1. How many more does he need?
He needs 3 puppies. Is that what you said?
Yeah.
Awesome. I'm pretty sure my kids would agree with something like that. They need them, yes. Yeah, so he needs something or wants to have something. Might be a little more accurate. And he already has so many. How many more does he need? All right, our last one, our number line or measurement model. So over here, what do you guys have for your number line measurement model?
So Mike wants to build a fence across his yard, and his yard is 25 meters long. He has already built 15 meters, so how many more fence does he?
Wonderful. Jordan.
Monica has made craving ice cream, and she has walked 10 miles to Brahms so far. Brahms is 17 miles away. How much more will she have to walk to get ice cream?
That's a lot of walking for some ice cream. Man alive. Okay. Yeah, so you had miles, you have feet. Both of those are measurement models because we have the ability to subdivide them, right, to break them into pieces. There's other things too besides distances you guys could use. Hey, guys. There's other things you could use for number line that are not actual distances as well, that have that same sort of feel to them. Anything that has the able to be subdivided. So you can think about like cups of sugar, right? Can I have a half a cup of sugar? I can. So it would make sense to actually use that in that context as well. So there's other components too, but you guys have a very good idea. All right, so we're going to do one more piece. We're going to do this next part where it talks about the properties of subtraction. And then that's where we're going to end for today so that we have time for our group work. So our question here is asking us the properties of subtraction. Which of these properties would actually hold? In other words, which ones exists as properties for subtraction? So if you'll remember, closure is the idea that if we take two values, in this case whole numbers because we're doing whole number subtraction, and we subtract them, because that's our operation now, will we always get another whole number?
Wait.
If you take two numbers, two whole numbers, and you subtract them, will you always get another whole number? Okay, so Reagan's saying no. So why? I'm sorry, Elizabeth's saying no. Why?
Well, if you have like 7, I already messed up.
No, you can use 7. Just find a different number for me. After 7.
I don't know what I was thinking. I was thinking 15 and then getting 7.5. I don't remember what I did.
How about like that? These are two whole numbers, right? What happens when you subtract these?
You get a negative.
You get a negative. Are negative numbers whole numbers? They're not. They're integers. So this is -8, which is not an element. You guys remember that symbol? Of the whole numbers. Now, if I switched the order and did 15 minus 7, I'd be just fine. But I have to be able to do it for every ordering, and I can't. So the whole numbers are not closed under subtraction. So this is not a property. Commutative. So you remember when we did commutative with addition? Commutative has the ability to take two numbers and add them together in either order and get the same thing. 5 plus 3 is 3 plus 5. Can I do that with subtraction? No, I can't do that. And if I use the numbers that I just used, I can tell you that 5 minus 3 does not equal 3 minus 5. In fact, it's exactly the wrong pieces that are failing on closure, right? It's the other half of them. So there's no closure property, and there's no commutative property for a subtraction. How about associative? So you might need to play with this a little bit. Associative is the idea that we can regroup parentheses. Remember that? So let me write one down, and we'll play with it a little bit to see what happens. We're going to do 3, 2, and 1. So I've got my grouping around the first two parentheses, or around the parentheses with the grouping around the first two numbers. Now I'm going to shift it and I'm going to put it around the second two numbers. Okay, there's nothing special about these numbers. They just are kind of nice, that's all. So if I do 3 minus 2, I have 1, and 1 minus 1 would be 0. So it's 0 on the left side. Over here on the right side, I'd have to start with the parentheses. 2 minus 1 is 1, and then 3 minus that 1 would give me 2. So I do not have the same value here either. So the associative property is a no-go. It does not hold. And the last one is kind of interesting. Do you remember the identity property for addition? What was our identity element? 0. 0 has this very nice feature that if I add it to anything, it doesn't change numbers, right? So 6 plus 0, 4 plus 0, 0 plus 7, all of them don't change the other value when I add 0. But the kicker is it had to work two-directionally. So while the identity property somehow seems to work if I subtract 0 from a number, right? This seems like it might be a contender. 0 would probably be helpful, right? But if I do it in the other order, it does not equal that same 7. So they have to work both directions for it to be an identity. 7 minus 0 and 0 minus 7. And it should be no surprise that this fails. It fails because it wasn't commutative to start with, right? So yeah, this one was definitely going to fail. And while there's no, in theory, we could use another number where I put the zeros. 0 is the only one that even works for half of it, right? 7 minus anything else will not continue to be 7. So 0 is the only possible solution, and it failed on the other direction. So there is no identity element, no identity property for subtraction. So basically, subtraction is propertyless, right? All the properties we just had fail for subtraction. All right, so we're going to pause there for today.